So, in the last module what we have seen? We have seen how we can use physical vapor deposition technique to deposit metals, to deposit semiconductor, to deposit insulators, right. Now, the next point or topic in this particular lecture or module is on chemical vapor deposition. So, before we go to the chemical vapor deposition, let us see one more technique. We have seen thermal evaporator, we have seen electron beam evaporator. Let us see one more technique called sputtering. So, my teacher, when she was teaching me, she gave an example how sputtering sounds like. Sputtering is similar to the effect of raindrop. You have heard the raindrop on a metal roof and you will hear that sound, right, and that sound is similar to sputtering. So, not exactly in terms of sound, but the point was that atom by atom you actually deposit on the wafer. That is the point, that by drop you have the rain, right. So, atom by atom you dislodge and you deposit on the wafer. So, dislodge from where? Dislodge from this source, So, that is your sputtering. Let us see in terms of how sputtering will look like. So, we have seen this thermal evaporation and e-beam evaporation. We have seen what is there within the chamber. Let us see this one, which is your sputtering. So, if you see this particular slide, what you see is that you have the target, which is your source, and you apply the voltage between the anode and cathode, right, and here you put your wafer. In the bottom you load your wafer, then what will happen, that when this is happening, when we apply a very high voltage and you introduce argon, what will happen, that the plasma is needed to make the gas conductive and generated ions can then be accelerated to strike the target. Target is bombarded by these ions, usually argon plus. The argon ions will bombard this target, as you can see here, there is a bombardment. Because of the bombardment of the target, the atoms will dislodge from your target and will start drop by drop, one by one, right, falling towards the target, and you can see a film getting deposited on the wafer, alright. So, what happens, ion knocks the atom from the target, right, which ions? Argon ions. Sputter atoms are transported to the substrate where deposition occurs, right. This is what we have right now discussed, and we are not going too deep into sputtering. That is why guys I am telling you about basic things, okay, basic things. Now, you see one thing here, what is difference in your thermal or e-beam and sputtering. What is the difference? That these two, thermal and e-beam, we have used a very high voltage, we have melted the metal or a semiconductor, and when we have deposited. In sputtering, we are actually dislodging the atoms from the target. So, when we are dislodging the atoms in this particular fashion, it is the mechanical way, of dislodging the atoms, alright. So, this is the mechanical way of dislodging the atoms, and that is why this is also called a mechanical way of depositing the film, anyway. So, wide variety of materials can be deposited because material is put into vapor phase by a mechanical rather than a chemical or thermal process, right. So, here because you are dislodging mechanically, you can deposit variety of metals, right, and we can also deposit alloys and insulators. So, what is the advantage here? The excellent step coverage of the sharp topologies because of high chamber pressure causing a large amount of scattering events as target material towards the wafers. So, what does that mean? That in this particular process, first is a very high chamber pressure is required. Second is means very sharp topologies are laid like this, and you want to coat this, right, coat this tab like this. Then sputtering is better, compared to thermal evaporation or e-beam evaporation. Sputtering is better compared to thermal evaporation or e-beam evaporation when you want to have a excellent step coverage of the sharp topologies. Okay. Next is the film stress can be controlled to some degree by chamber pressure and RF power, but you see there are several types of sputtering. Okay. DC sputtering, which you can see here, then there are RF sputtering, then there is RF magnetron sputtering, RF magnetron sputtering. Okay. So, point is you can change the chamber pressure, you can change the RF power, and your stress can also be controlled, your film stress can also be controlled. Okay. So, what we have understood? We understood that there are 3 ways of physical vapor deposition mainly, and that 3 ways are thermal evaporation, e-beam evaporation and sputtering. Here you can see the equipment, which is a sputter deposition, Here you load the wafer and you can change your voltage and power using this particular section, right. This is connected again to the vacuum pump, which is your turbomolecular pump, Okay. Nothing but your turbomolecular pump. There are vacuum gauge to measure the pressure, and then there is a RF source or DC source based on either it is RF sputtering or it is a DC sputtering. You can load, you have to load the your source, which is a plate, onto the source holder like this. This is your material, alright. This is your material, and this plate you can load on the source holder. Now, when the argon ion is inserted at a very high RF voltage or RF power, they will strike, the ions will strike this source and dislodge the atoms from this source, which will ultimately get deposited on the wafer that is kept on the substrate holder, that is loaded on the substrate holder, alright. Point is that we have 3 ways of depositing the materials. First is your thermal evaporation, second is your e-beam evaporation, and third is your sputtering, alright. So, let us move to the next one, which is your chemical vapor deposition. Now, chemical vapor deposition is used in several formats. What does it mean? That let us see one by one. Chemical vapor deposition, also called as CVD, is a formation of non-volatile solid film. What is volatile and what is non-volatile? All right. So, if you see, all of us have visited at least a gas station, right? Gas station, or we also call here petrol pump, right. Now, when we go to gas station or petrol pump, we feel a smell of petrol or diesel, right. We feel a smell of petrol or diesel. Why there is a smell? Because when you drop a drop of a petrol, that means once the petrol is on the surface, what will happen? It will start evaporating, all right. That means that the petrol is volatile, all right. That is why we can smell it. It starts evaporating immediately at room temperature, right, at a normal temperature it starts evaporating. What are other kind of volatile organic compounds? If I ask you, then you can immediately say what are other kind of volatile organic compounds? Ethanol. acetone, methanol, butanol, isopropyl alcohol, right, kerosene, diesel, petrol, this everything is volatile. It will evaporate, it will vaporized, right, vaporized at room temperature, alright. So, when we talk about chemical vapor deposition, what is written? Chemical vapor deposition is a formation of non volatile solid film, that means it is not volatile, once it is deposited it will stay, that is non volatile, alright. So, I was just showing you the difference between volatile and non volatile. Now, we know that CVD is formation of non volatile film on a substrate by the reaction of vapor phase chemical reactants that contains the required constituents. That means, the chemical reaction that we are working in the, or we are using onto the substrate, right, the reaction that happens onto the substrate because of the chemicals, that chemical would contain the required constituents. Required constituents is the material which we want to deposit on the substrate as a solid film, okay. Now, the reactant gases are introduced into reaction chamber and are decomposed and reacted at a heated surface to form the film. So, what will happen? We have to introduce a reactant gas into a reaction chamber, and then there is a chemical reaction because of which decomposition happens. When decomposition happens, this chemical reaction has to be done at some heated surface, right, and then the film formation, you will be observing a film formation. Again, this is a thin film technology, that is why we always say thin film, alright. Thick film, I have told you in the first class, I have shown you the example screen printing, alright. So, what are the kind of chemical vapor deposition? See, it is mind boggling. There are so many kind of chemical vapor deposition. You can start with atmospheric pressure CVD, low pressure CVD, plasma enhanced CVD, metal organic CVD, photochemical CVD, laser CVD, chemical beam epitaxy, chemical vapor infiltration, so many things or so many kind of CVDs, right. What we have to see here is two CVDs, one is low pressure chemical CVD, another one is plasma enhanced chemical vapor deposition or CVD, alright. So, low pressure CVD is nothing but low pressure chemical vapor deposition, plasma enhanced is plasma enhanced chemical vapor deposition, alright. So, these two we will see, and we will see that which one we can use when, So, if you go to the next slide, same slide, this is how the CVD system is, right. You have an high energy heated plasma, right. This is a substrate, this is a chamber, everything is in the inside the chamber. I will show it to you an example here, and then there is a source gases that we have introduced, and there is a reaction occurs on the substrate, right, and then the product, the not useful gases, right, the gases that are byproduct of this particular reactions that are thrown out of the chamber, alright. So, the point is you have to apply a high energy heat plasma, the substrate is heated or it is kept at low heat, that is the temperature is around 100 degree centigrade to 500 degree centigrade. In some cases it is at very high temperature 1200 degree centigrade, we will see depending on the type of CVD the temperature also changes, alright. The point is that you have the substrate, you have the reactor, and then you introduce source gases, and the byproducts or gaseous products will we have to throw out of the chamber. It is not in the air, okay, it is just out of the chamber to the proper processing lines. Okay. So, when we talk about Lpcvd, it is similar to what you have guessed already. We have seen this Lpcvd for wet and dry oxidation, we have seen this Lpcvd in wet oxidation, we have seen this Lpcvd in dry oxidation, correct. That is why Lpcvd or low pressure chemical vapor deposition can be used for uniform film thickness because of the low deposition rate. You have seen that, right. In dry oxidation we can only have few nanometers and or 0.1 micron, that is I think the maximum. In wet oxidation it can be 1 to 2 microns, right. So, the deposition is extremely slow, and that is why the thickness would be the film thickness would be more uniform compared to PVD. Wafers are stacked vertically facing each other. You know this particular tube, right? What is it? It is a horizontal tube, because tube is in horizontal direction, and then it is kept in the furnace. So, horizontal tube furnace, you can see horizontal tube furnace, right. And we also know that this material is nothing but your quartz. This material is your quartz. The reactant gases you insert in here, the exhauster gases are out, right. You have put the wafer stacked in the vertical facing to each other, right, vertically facing, you can see here, right. Now, gas pressure is around 1 to 1000 millitorr, and lower pressure means higher diffusivity of the gas to substrate. Then another advantage of CVD, Lpcvd, better step coverage, film uniformity and fewer defects, alright. But in case of Lpcvd, the temperature at which we perform this experiment or we use this tool is greater than 700 degrees centigrade. In case of silicon dioxide, we have seen it is 1150 to 1200 degrees centigrade, right, 1150 to 1200 degrees centigrade. So, the temperature is extremely high, okay guys, temperature is high. Now, what is another type? Pecvd. So, the system will look like this. Lpcvd, Pecvd system is like this, right. This is the chamber in which the reactants will occur, and you can see here, you can see the plasma generated. Here you can load the substrate, which comes over here. You can lift it, you can put the wafer, and the wafer will go in this particular direction. It will load onto the substrate, and then there is generation of plasma. The chemical reactions will deposit the material on the substrate, alright. So, how things happens within this particular system, in this system how the process happens. You can also see there is a vacuum pump. Here also we require a vacuum, but of a low order, alright, not like in case of PVD that we require very high pressure. Here is a low order vacuum. So, plasma NNCVD, plasma helps to break up gas molecules, 1, able to process at low temperature and pressure, and that is why the application is electronics on plastic. Why? Because if I use plastic at 700 degrees centigrade or more, what will happen? Correct, it will burn. But if I want to use, or if I want to have flexible electronics, and if I want an insulator film or insulating film, then I can use plasma enhanced chemical vapor deposition, right. Another example that I gave it to you when I was teaching you about gas sensor is, if I have a aluminum, right. Now, suppose you have oxidized silicon substrate on which you have a aluminum or pattern, let us say this is aluminum, right. On this you want to grow silicon dioxide, then you cannot use Lpcvd because the temperature is greater than 700 degrees centigrade, but we can use Pecvd because the temperature is low. Low is how much? We can deposit the film or we can grow the film at 100 degrees centigrade also. We can deposit the film even less than 100 degrees centigrade, okay, less than 100 degrees centigrade. Anyway, so the point is that Pecvd comes at a rescue when you want to have electronics on plastics, right. Pressure higher than in sputter deposition, less ion bombardment on substrate, and more collision in gas phase, alright. Can run in RF plasma mode, avoid charge buildup for insulators, that is the advantage. Film quality is poorer than Lpcvd, film quality is poorer, but temperature is low. The wafers had to be laid down horizontally side by side, in this case vertically, in this case horizontally, right. So, Lpcvd vertically you have to load the wafer, Pecvd you have to load the wafer horizontally, alright. Now, if I want to see the advantages and disadvantages of chemical vapor deposition over physical vapor deposition, if there is a question, that when I compare a CVD with respect to PVD, what are the advantages of CVD over PVD, what are the disadvantages of CVD over PVD, alright. So, first the first advantage is good reproducibility and high growth rates possible. We can reproduce a film much more accurately and with higher growth rate compared to PVD. Second is can deposit material which are hard to evaporate. You see, you can deposit material which are hard to evaporate, that is why what we are depositing silicon dioxide, what we are depositing silicon nitride, SiO2, Si3 and 4. These are the materials very hard to deposit, alright, means very hard to deposit via evaporation. But if I use CVD, it becomes, my life becomes easy. That is why you can use or deposit material which are hard to evaporate. Next is can grow epitaxial film, in this case also called Vapour epitaxy. For instance, metal organic CVD is also called organometallic VPE, Vapour phase epitaxy. We have not seen that, so do not worry about it. Generally better quality film quality, more conformal step coverage. Step coverage is better in case of CVD when we compare with respect to PVD, right. In case of CVD, the step coverage is better compared to PVD. What are disadvantages? Disadvantages, first disadvantage is high process temperatures, Second disadvantage is complex processes, corrosive and toxic gases, right. High process temperature is greater than 700 degrees centigrade, right. Toxic and corrosive gases, you see. So, you had to be careful. Film may not be pure hydrogen incorporation, this you always remember, right. We have talked about the hydrogen incorporation when we use wet oxidation. We have seen, right, advantages of dry and wet oxidation. What we found is in wet oxidation the growth is higher, however, there will be pores in because of the hydrogen incorporation, and that will cause a problem in your MOSFET. That is why we do not use gate oxide using, we do not grow gate oxide using wet oxidation, alright. So, these are some of the advantages and disadvantages of CVD over PVD, and now let us see what we mean by the step coverage. What we mean by step coverage? You see here carefully, right. When I use evaporation, you see I can cover this area, I can cover this area, I can cover this area, but my this area is not covered, this area is not covered, alright. This is a step, right. What I am talking about is a step. What I want is, I want that I should have film which can cover the entire step like this, right. So, what I see first in evaporation, I can cover this, I can cover this, I can cover this, I cannot cover this area. Now, if I talk about sputtering, somewhat this area, you see until here, you see from here till here, but it is not covering completely, right. But if you talk about CVD, about chemical vapor deposition, you can see a perfect or better step coverage compared to the PVD. Now, there is lot of physics behind it, what is the angle, why we have to keep the wafer at 90 degree with respect to source, but that is not our objective to understand the details about that. Our objective is to understand that if you are given equipment, which equipment you can use for depositing or growing metal, semiconductor or insulator, alright. That is the interest. So, now what we have seen? We have seen PVD, we have seen CVD, in CVD we have seen Lpcvd and Pecvd, right. So, I hope that you understood what is PVD, I hope you understood what is CVD, I hope that you understand how we can or you understood how we can deposit the metal using thermal evaporator by heating it, by using E beam, by incidenting the E beam using the magnets, right, and the E beam generator. Then we have seen the comparison between E beam and thermal evaporator. Then we move on to the sputtering, and we see that we have to insert the argon gas. The argon ions will bombard on the target or the source. The source, on bombarding the source, the atom from the source will be dislodged, will get deposit on the substrate. Then we have seen advantages of sputtering, that it can practically deposit any material. Then we have seen chemical vapor deposition. In chemical vapor deposition, what we have seen, there is a lot of CVDs, but what we are interested in understanding, 2 CVDs, one is Lpcvd, one is Pecvd. Alright. Then we have compared, if you have to cover a step, which one would be better, Lpcvd will be better, or in general CVD would be better, or sputtering would be better, or thermal evaporator would be better. That is what we have done until now, right. So, now you are able to understand, if you have a silicon, you can grow oxide, on the oxide you can deposit any material, right. In the next class, let us understand photolithography. Once you understand photolithography, that will be end of understanding the process. Then using this process, using this knowledge that we will acquire, right, we will see how we can fabricate our MOSFET, how we will fabricate our MOSFET. Okay. So, read this particular slides what I have taught you today, understand it, and let us see how photolithography can be used, and we will take an example. We have already taken an example in the earlier class. We have taken an example of an IDE within SU8. We have taken an example of an gas sensor. Alright, but we will quickly take an example. So, you finally at the end of photolithography, you will understand how you can use these steps that we have learned to fabricate a device. Alright. So, I will see you in the next class. Let us learn in the next class what is photolithography. Alright. So, till then you take care.